Welcome to the lesson on momentum. Momentum is a word in our everyday life that has many different connotations depending on the context in which it's used. We, of course, in this lesson are going to focus on the physics context of momentum, and that being that momentum is the characteristic of an object that depends on its mass and velocity. Students often mistake momentum as a force. It is not a force. They often mistake momentum as energy, and is not energy. Momentum is the unique characteristic of an object that is the product of its mass and velocity. Our symbol for momentum is lowercase p. Make sure you don't get sloppy with your p, as capital P is power and lowercase p is momentum. And since it's a product of mass and velocity, mass is m, velocity is v, so p equals mv. We also see that the units here, based on our product of mass and velocity, mass being kilograms and velocity being meters per second, that the unit of momentum would be your kilogram meter per second. Another quantity in our study of momentum is the quantity impulse. Impulse is the force that acts on an object times the time in which that force acts. Impulse, the symbol of which is capital J, then would be F times T. So capital J equals F times T is the equation for impulse. The unit for force is Newton, the unit of time is second. So our units of impulse are Newton seconds, not Newtons per second, but Newton seconds. We can also see that if we tease apart the Newton unit, we see an interesting relationship here. Remember from our study on Newton's laws that the Newton is the unit of force, and which is the product of mass and acceleration, F equals ma. So what we could also write for Newton is the kilogram, the unit of m, times meter per second squared, the unit of a. Now when we take and multiply by time in seconds, what we see is that seconds cancels out the square in the denominator of the meter per second squared, and what we get is the kilogram times meter per second. And what we notice here is that is the same as the units of momentum. This segues nicely into our next part, which is called the impulse momentum theorem. Probably one of the two most important concepts in our study of momentum. This, of course, being the impulse momentum theorem, is that the impulse that acts on an object is equal to that object's change in momentum. Now, anytime we throw a delta in front of a quantity, meaning change, that means something used to calculate that quantity had to also have changed. P is the product of mass and velocity. So that means if there's a change in momentum, that has to mean there was a change in mass, or a change in velocity, or a change in both. Therefore, as our equation progresses here, what you see is that we've taken the equation for impulse, F times T, and substituted it in place of J, and that we have options here as far as our substitution for delta P. The majority of the time, the application here on the impulse momentum theorem will be that you have a mass that doesn't change and remains constant times a velocity that does change. So the impulse momentum theorem would be Ft equals m delta v. There are times in which we could have a change in mass times a constant velocity. An example here would be, for example, if you were pulling a cart in a rainstorm and you were pulling the cart at constant velocity. That cart's momentum is still changing because it's taking on appreciable water, therefore changing its mass over time. We have never seen in our study in AP Physics where both the mass and the velocity both change. So you've seen that left off here. But it is certainly possible that you could have that in calculating and doing a calculation with the impulse momentum theorem. A quick side note here. If we take and divide in this middle equation here, Ft and m delta v, both by time, what we see is that the time units cancel, and you should recognize probably that change in velocity over time is acceleration. So we're left with F on the left side of our equation and m times a on the right side of our equation. In Newton's original manuscripts in which he published his laws of motion, Newton's second law actually first appeared as Ft equals m delta v. Then as time progressed, both sides were divided by t, and his second law became known from an equation standpoint as F equals ma. Okay, next we're going to take a look at two of the primary applications of the impulse momentum theorem. And the first, and probably the most widely studied in this, is the car safety application. What we're going to do is we're going to pause our lesson here and take a look at a video. I'll probably likely talk during that video and maybe even pause it along the way at some point and talk about the purpose of car safety, and then come back and see how it relates to the impulse momentum theorem in the equation that we have here in this lesson. More to come here in a second. What we have here is a video from the Insurance Institute for Highway Safety, and what you're going to see here are several videos in a row on this crash test dummy. And this is without a seat belt. That was without a seat belt and an airbag. Now is with a seat belt and an airbag. And pretty soon here, they're going to put them both in one video over the other, which is right here. All right, let's pause it here for a moment and talk about what is the ultimate purpose and goal of car safety. The ultimate purpose and goal of car safety, of course, is to keep the occupant safe, you might say. But it's not the physics goal. The physics goal is to reduce the force that's acting on the occupant during the collision. So we want to get that force acting on the passenger as low as possible. Because if we do that from a physics standpoint, what we're going to do is obviously increase the opportunity for them to survive that crash. Now, you'll notice in both these videos, and I'll let that play through here for the last 10 seconds or so in a moment, but in both videos the cars are identical. They're crashing the cars into the wall at the same speed, and both cars come to rest. So being the occupant of the car, both occupants are also traveling the same speed of the car and will also go to rest. What that says to you is that for the video on the top without safety and for the video on the bottom with safety, both occupants are undergoing the same change in velocity. At the moment, neither one of them and neither one of the occupants have had their mass changed due to this event. However, what that says to you then is the right side of the impulse momentum equation, which we'll take a look at here again in a second, there's no change to that right side. There's no change in mass when we compare these two events, and there's no change in velocity. Both events have the same mass and have the occupant undergo the same change in velocity. Back to the focus and the goal. From a physics standpoint, what's the goal? To reduce the force acting on the occupant during the crash. All right, so we're going to finish playing this out and then back to the other lesson here in a moment. Okay, as mentioned while we were watching that video, in both situations, the change in velocity of the occupant is the same. Neither one of the occupants loses appreciable mass during the event, so there's no change in mass. The goal of car safety is to reduce the force, so how will we do that? What we're going to do is we're going to have that change in momentum try to take place in over a greater amount of time. There's the reason for the airbag and for using, especially for the airbag and for the seat belt. What the airbag and the seatbelt do is they cause that occupant's change in velocity to take place over a greater amount of time, therefore reducing the force on the occupant and hopefully giving them a chance to survive the crash. Okay? All right. The next application of the impulse momentum theorem is in the application of sports. In the next video clip, we're going to take a look at a golf ball that's being struck. I may also pause that during that and show you a couple things there. And we'll talk about what is the physics purpose in sports in which there's contact with objects and how it relates to the impulse momentum theorem. The goal in any sport in which objects are struck, such as golf, baseball, kicking a soccer ball, hitting a volleyball, hitting a tennis ball with a racket, the physics goal from that standpoint is to change the velocity of the object greater than your opponent, therefore hopefully increasing your chances of being successful. No better illustration here than with golf. And it should be clear to you that as a golfer off the tee, if you are able to change the velocity of the golf ball greater than your opponent, that means and results, as we probably can guess from our study in kinematics, in a greater distance for that ball being hit. Now, obviously that's not all that goes into it. There's accuracy and things like that to take into consideration. So there's other points to the drive as well. But basically from a physics standpoint, we want to change the velocity greater for this object being struck than our opponent does. Okay? All right, so if we take a look at this video real quick. What was really neat, if you saw that distortion, and go back if you need to see it, the distortion of the golf ball being struck. Okay, and now we're going to go back to our lesson here and take a look at how all the variables play into with the relationship to the impulse momentum theorem. From the standpoint of the impulse momentum theorem, what we just got done discussing is that the physics goal in sports for those objects being struck is to change the velocity of the object as great as possible. We know the actual mass of the object doesn't change. So what are the two ways that we can impact and have a greatest change in velocity as possible? Well, one of those is to strike the object with greater force. This is done by athletes working out, getting bigger and stronger. And the other way to do it is to increase the amount of time in which the object that you're hitting it with is in contact with the object. This, in the context of the golf or the baseball, for example, is done by swing speed. So if you can swing your club faster or swing your bat faster than somebody else, that means the ball will remain in contact with the club or the bat for a longer amount of time, therefore imparting greater change in velocity on that object. Okay, so there's your two primary applications on the impulse momentum theorem. Now we're going to move on to the other major concept in this unit, and that's conservation of momentum. And conservation of momentum, simply stated, is that the momentum before the collision is equal to the momentum after the collision. Okay? And we're going to work a lot on this with regards to different types of collisions, etc. And the two types of collisions are the elastic collision and the inelastic collision. An elastic collision is one in which both momentum and kinetic energy are conserved. In an inelastic collision, momentum is conserved, but kinetic energy is not conserved. So what you hear is that for both collisions, momentum is always conserved. However, for the elastic collision, kinetic energy is conserved, and for inelastic, it is not. So you can have partially inelastic, total inelastic, and we'll be working much more on that with problems in class.